Hello friends, welcome to Risingpearl.com. We are talking about series 13 where we are learning a lot on surface areas and volumes. Friends, this is webisode number 17 and we are going to continue to find out how to solve questions on volumes of combination of solid figures. This is part 3. It was webisode 15 where we started the part 1 on these type of questions. That is, you're going to be given a combination of solid figures and you have to find out the volume. So let's find out how do we solve these questions. We talked about this over and over again. So whenever you're dealing with a combination of solids, what is the fundamental difference between finding out the area and finding out their volume? So now whenever you are actually looking at calculating the area of a combination of solid figure, we do not always just add the areas of the parts that make up solid. Why don't we simply add all the areas together? Because some parts of the area, they disappear. As we combine, as we join the parts, what happens is some of the parts of the solid, they disappear. So we cannot simply, whenever we are finding out the area of a combination of solids, we do not simply add the areas of the individual components, because some areas, they disappear as we join the parts. So now what about the volume? Now when it comes to the volume, when it comes to calculating the volume of combination of solid figures, we almost always add the volumes of the parts that make up the solid. We almost always add the volumes of the parts that make up the solid. This distinction, friends, is very important to keep in mind. So each star is representing varies. It's very important to keep this differentiation in mind as you solve these questions that involve combination of solids between finding out areas and finding out the volumes. So let's take a look at some examples. A juice seller was serving his customers using glasses as shown in the figure below. Well, where is the figure? So let's get some figure. So let's say, so we have two figures here. The inner diameter of the cylindrical glass was 5 centimeter, but the bottom of the glass had a hemisphere raised portion which reduced the capacity of the glass. So obviously he is a juice seller, so he is selling juice, right? He is a juice seller and he is selling juice in a type of glass. Normally you will expect the glass to look like this. So where you have a cylinder, right? This is the cylinder part, this is the cylinder, and this is the hemisphere. The inner diameter of the cylindrical glass is 5 centimeter, but the bottom of the glass had a hemisphere. It is hemisphere or hemispherical raised portion which reduced the capacity. So instead of having the glass like this, as you will imagine, or maybe just a cylinder, the glass does not have a hemisphere like this. Instead, it has a hemisphere which is upside down. So in other words, the hemisphere actually is upside down, which, as you can see, reduces the overall capacity of the glass, right? So now the hemisphere, because it is like this, so this much amount of volume is not available for the juice, because this is the hemisphere part of the glass which is reducing the capacity of the juice that we can pour inside the glass. Now let's see what all dimensions are given. So it's very important, friends, as you read the question, that you should be able to clearly visualize this in your mind, that we are dealing with a cylinder. So clearly there is a cylinder, right? And in addition to that, there is a hemisphere. But the way the question is given is that the hemisphere is in such a way that it does not actually add to the capacity. So our figure has a cylinder and a hemisphere, but our hemisphere is given. So if the hemisphere were like this, it actually would have increased the capacity of the juice, right? Because this one, let's call it first, and this is second. So the capacity of the cylinder is 1, this is 1, and then this is a hemisphere which is 2. If the glass were such that the capacity increases, then what we do, we take 1 and we add 2 to it, right? This becomes the final capacity of the juice glass. But in the question it is given, the bottom of the glass had a hemispherical raised portion which reduced, this is the key word, which reduced the capacity of the glass. That means our hemisphere is upside down. So our volume will be 1 minus 2. And it is because of this reason that I mentioned, when we are dealing with questions on capacity is nothing but volume, that almost always we add the parts, but there are examples where questions where we actually subtract the volume. So this is a question where if this is the capacity of the cylinder and if this is the capacity of the hemisphere, the final capacity that I can pour, the amount of juice I can pour will be 1 minus 2. Right? So let's actually go ahead and solve this. Let's clean this up a little bit. So the question is, now let's find out what is given. So this is a hemisphere. We need to know the radius. Similarly, this actually is the height of the, this is the height of the cylinder. And this is the radius of the hemisphere, which is the same as the radius of the circle. So let's see. So the inner diameter is 5. So R, so let's write it here. So twice R, 2R is equal to 5 because the diameter of the cylindrical glass is 5. So 2R equals 5. If R is the radius, 2R is the diameter. So from here we get R is equal to 5 by 2 or simply 2.5. So the radius is 2.5. So we know this is 2.5. Now what do we know about the height? If the height of the glass is 10 centimeters, so the height of the glass is also given, which is 10 centimeter. That means this height is 10 centimeter. So now, so if volume of cylinder is 1, so volume of cylinder, we know the formula how to calculate the volume of cylinder. It is pi r square h. We know r, we know h, so we can find out the volume, and let's say this is 1, correct? Now volume of hemisphere, volume of the hemisphere will be equal to, it will be 2 by 3 pi r cube. This is 3 pi r cube, and we know the value of r, which is 2.5. So this, if we call this 2, then so the question is, find the apparent capacity of the glass and the actual capacity. So the apparent capacity is from outside. What does it look like? From outside it looks like the capacity will be the volume of the cylinder, right? Because from outside, because this is raised from inside, if you look from outside, you're going to just see the curved surface, right? So you will think from outside, which is apparent capacity, which is visible to the common eye, you will think from outside the capacity is the volume of the cylinder. So if you just substitute R equals 2.5 and H equals 10, and you will find out the volume, which is the apparent capacity of the glass. But what is the actual capacity? So the actual capacity, like we discussed, so in real life the actual capacity is the amount of, actually what is the volume, that will be 1 minus 2. So again, simply putting the value of R and H and R here, you can find out 1 and 2. You subtract 2 from 1, you will get the actual capacity.